In this video, I will go over the homework that follows the lecture 14.1 that is dedicated to the topic of midpoint approximation. And as always, I hope that you watch this lecture, and let's jump right ahead into the homework. And the first question, we have to use the midpoint approximation with two rectangles and estimate the area under the curve on the interval from -3 to 1. And let me go ahead and take a snapshot of this graph, and I'm going to bring in the picture so we can analyze it. I think I lost where did I draw that number 1? Oh, right there. All right, so the question is to use the midpoint with two rectangles, and to start we're going to consider that interval from -3 to 1, and my A is equal to -3, my B is equal to 1, N is the number of rectangles is 2, and therefore we can immediately compute delta x using this formula. It will be 2. 1 minus -3 is 4. 4 divided by 2 is 2. And we can create the partition here by adding delta x, starting with the leftmost point. So this is our partition. So -3, -1, and 1. So this is going to be my x0, x1, and x2. And to find the midpoint, use the midpoint approximation means we're looking for M2, and to use the midpoint means we're going on each of these intervals to use a rectangle constructed in the following way. We're going to find the midpoint, and we're going to look at the output of the function at that midpoint, and we're going to construct a rectangle with the height equal to the output of the function at the midpoint. So this is what it's going to look like. Now, my first midpoint will be -2, and my second midpoint here will be 0. So to finish this problem, all we have to do is to compute the area of each of this rectangle, which both are equal to the base times the height, but since they all have the common base, which is delta x, it can be factored out, and the height of each of the rectangles can be expressed as the output of the function at the midpoint. So symbolically we can express the area like this, and now plugging everything in, what do we get? F of -2 is 2, f of 0 is 5, so the answer is 14. All right, so let's move on to the next question. In this question, we're given an interactive problem, so there isn't much for us to write over here. So let's just carefully read the problem. It says use the midpoint approximation. So A is -5, B is -2, N is 3. So we can just for practice compute delta x. So it's going to be B minus A over N. So in this case, it's just going to be 1, and we're looking for M3. So M3 will be equal to delta x, and here we're going to take f of the first midpoint, which is the average of x0 and x1, and so on. So I'm just writing the general formula, but we're not going to use that formula here because we are given a graph and an ability to interact with it. So we're going to choose a to be -5. We're going to choose b to be -2. We're going to choose n to be 3. It's actually pretty cool. And we're going to drag these points, and it looks pretty accurate. I don't know how accurate it has to be, but it looks pretty accurate to me. And let's go ahead and submit this, and that's correct. In the next problem, we are actually given a function so we're going to identify all the key ingredients -2 minus -6 is 4. 4 divided by 2 is 2. And so we can draw some random graph to represent our graph on the interval from -6 to -2. So for example, this is -6, this is -2, and since we only have two rectangles, this is going to be -4, and we have some, let's say, random function, and if we're going to be using the midpoint, so we're going to be evaluating the function at -5, and we're going to be evaluating the function at -3, so the M2 will be equal to delta x times f of -5 plus f of -3. And of course, if you like doing this by hand, you can just find f of -5. So you may pretty much, you kind of asking yourself to evaluate this function at -5 and -3. At -5 it will be 25 over 4 plus 1, it will be 29 over 4, and at -3 it will be 13 over 4. So we're going to do it like this. And 29 plus 13 is 42. So we have 2 times 42 over 4, which is 21. However, you can always make your life a little easier by using technology. And let's go over this problem real quick with technology. So we can always introduce this function, whatever the function is, and we can always introduce some values a and b, and in our case a is equal to -6 and b is equal to -2. So we're literally trying to estimate the area under this piece of the parabola. We can help ourselves with computing the delta x by using this formula. So n is 2 in this case. And yeah, so we pretty much, if we label this, let's just call it d for delta x, then m2 will be equal to delta x times f of, and here again, you can use technology, and instead of actually figuring out the value -5, you can do the average, like -6 plus -4 divided by 2 plus f of -4 plus -2 divided by 2, and it certainly kind of takes the pressure off, the computational pressure off, and allows you to perform, or rather it allows you to focus on the actual task rather than being worried about whether you computed it right or wrong. So the answer is 21. And let's move on to the next question. So here we have another parabola. The interval is given. The number of rectangles is given. Delta x is computed using the formula. And we need to visualize the interval. So it goes from -5 to 3. So 1, 2, 3, -1, -2, -3, -4, -5. So we have -5, -4, -3, -2, -1, 0, 1, 2, 3. And we need to visualize the partition. So we have 4 intervals. So it goes from -5 to -3 to -1 to 1 to 3. So this is going to be my x0, this is going to be my x1, x2, x3, and x4, but these are my midpoints right here. All right, so this is going to be my first midpoint, this is going to be my second midpoint, my third midpoint, and my fourth midpoint. So whatever the graph is, I'm going to be approximating the area underneath the graph using these rectangles. Of course, if we want to write this out symbolically, we're going to have m4 being equal to delta x times f of x1 star f of x2 star plus f of x3 star, and finally f of x4 star. And in our case, it will be 2 times f of -4 plus f of -2 plus f of 0 plus f of 2. I'm just going to use Desmos. So my f of x is x squared over 10. My a is -5, my b is 3, n is 4, and here, again, Desmos is a tool, so let me use it as a tool. Since I already defined all the functions, I'm just going to type here f of -4 plus f of -2 plus f of 0 plus f of 2. And the answer is 4.8. All right, making some progress. In question number 5, we are asked to find the upper bound for the error. And what we are actually asked to do here is to use the formula that we discussed in this lecture. And just to bring it in front of us, here's the formula. So the formula for the upper bound of the error in midpoint approximation is the following. And let's go back to the problem. We are using midpoint, so if we're approximating this with a midpoint on 2 intervals, then looking at the boundaries of the integral allow us to identify a and b. N is given to be 2. So the only thing that we don't know in this formula is the value of k, but k is the upper bound of the second derivative of the function on this interval. And you can find k analytically by differentiating your function. So for example, if you're, in this case, f of x is equal to 4x cubed minus x squared plus 2x, then f prime of x is equal to 12x squared minus 2x plus 2, and the second derivative will be 24x minus 2, and 24x minus 2 is a linear function, meaning it increases on the entire interval from 2 to 3, so its maximum value will be obtained at 3. So plugging in 3, we get 70. So that means we can set k to be equal to 70, and that will give us the strictest upper bound for this error. However, what I was going also suggest is introducing a new function. In this case, let's just reintroduce f of x. So we have f of x is 4x cubed minus x squared plus 2x. And you can totally use Desmos to find the second derivative of this function. And again, we probably want to do restriction on the domain. And now what we see in here, this is the graph of the second derivative. And the question is, where is its maximum value? And you can see here that the maximum value is at 70. So that could be one way to find k, or the upper bound of the second derivative. Now we have everything. So the upper bound for the error in this midpoint approximation can be computed by plugging in 70, b, a, n, and we can do this by hand, but there's nothing wrong with using technology. So 73 minus 2 cubed, that's just 1, and we have 24 times 2 squared. So the answer is 0.2, or rather 0.729167. And we were asked to round to the nearest hundredth, so we're gonna put 0.73. We are asked another question of the same nature. So here, let's just write what matters. A is equal to 0, b is equal to 2 pi, n is equal to 3. So I don't know k, but I'm about to find it because f of x is given to be cosine of x. So that means the first derivative is negative sine of x, and the second derivative is negative cosine of x. And last time I checked, negative cosine of x on the interval from 0 to 2 pi takes the largest value 1 and the smallest value negative 1, meaning its absolute value, the absolute value of the second derivative, the bound for the absolute value of the second derivative is 1. So we can choose k to be equal to 1, and we can now plug in all the ingredients into the formula. So we have 1 times 2 pi minus 0 cubed divided by 24 times n squared. And to compute this, again, I'll use the Desmos calculator. So we're going to have 1, 2 pi, 0, 3. So it's going to be 1.14838. And I'm pretty sure we had to round to nearest hundredth, so the final answer will be 1.15. It's a very similar question. A is equal to pi, b is equal to 3 pi, n is equal to 3, k we don't know, but we're going to find out because f of x is equal to sine of x, f prime of x is equal to cosine of x. The second derivative again is negative sine of x, and last time I checked, negative sine of x on the interval from 0 to 2 pi obtained the minimum at negative 1 and the maximum at 1. So the upper bound for the second derivative is 1. And now we can plug in all the ingredients and find the upper bound for the error. And it's going to be 1 times 3 pi minus pi cubed divided by 24 times 3 squared. And it looks like it's just going to be, it looks like it's the same exact calculations. So it's going to be the same exact answer. let's do another one. The lower bound is -2 pi, the upper bound is 3 pi, n is equal to 5. K, we don't know what k is, but we're gonna find it. So the function is sine of x plus cosine of x. The first derivative is cosine x minus sine x, and the second derivative is negative sine x minus cosine x, and it is not a it's not an obvious fact, but it is true that this can be written as, let's see, it's going to be square root of negative square root of 2 sine of x plus pi over 4. And let's check that. So we're going to graph the negative sine of x, negative cosine of x. That's the graph in red. And we're also going to graph square root of 2 sine of x plus pi over 4. And I need to put the negative in the front, right? So it is the same graph. And you may wonder, why is that we want to write it like this? Well, because sine ranges between 1 and -1. But when you multiply it by negative square root of 2, that means now it ranges from negative square root of 2 to square root of 2, right? So, and that means the second derivative, the absolute value of the second derivative, the largest it can be, is the square root of 2. So we're now ready to plug in all the ingredients into the formula. So we have the k, I almost forgot what it was, k times b minus a divided by 24 and squared. And k is square root of 2. So I'm going to use the Desmos calculator here. Square root of 2, 3 pi minus negative 2 pi, 24, 5 squared. So the answer is 9.135, which we're going to round to 9.14. And it seems like we completed this homework, so if you have any questions about midpoint approximation, feel free to reach out.